All right, welcome everyone. Today it is my pleasure to introduce to all of you Rajiv Kalia, a professor of computer science, chemical engineering, material science, as well as physics and astronomy at USC. And his multidisciplinary research concentrates in the areas of biophysics and material science. And his group is currently involved in computational synthesis and characterization of novel layered material architectures. So today he will tell us about deep learning models for material simulations and experiments. So please welcome Rajiv.
Well, thank you very much, Satish. So what I will do is, I will first describe to you the overall effort in our group in the area of materials simulations. And these are very large scale simulations. So, we are sort of data rich. And the question is, how to mathematically model the data, okay? And the second thing, which is turning out to be very exciting, is that there is a large variety of experiments, okay, in material science, especially using two probes. One is, electron microscopy, and the other one is X-ray diffraction. With these two probes, one is able to obtain a very large amount of data on a variety of very interesting materials and devices. And the thing is that these experimentalists are not using that data at all. They, extract some features and, they describe some physics, but a lot of the data, they are not able to model. And I think that's another area, okay, where I think deep learning can be very, very useful, okay? And so those are the two themes I will try to focus on: material simulations and experiments. So let me first give you an overview, okay, of the kinds of things, we do. So the first, I'll go from the left to the right, from top to bottom. So the first one is nanoenergetic materials. And these materials are things like nanoclusters, metallic nanoclusters. And in this one, this aluminum nanocluster is getting oxidized. And this is used as a device, okay? And it turns out that this particular application played a vital role in getting us a lot of funding. Okay. So the second one is a nanocomposite. In this case, the nanocomposite consists of ceramics. So the red part is silicon nitride ceramic, and inside the yellow one are fibers of silicon carbide, and it's a really very, very strong composite. And we have done modeling of that. The third one is quantum dots. As you know, quantum dots have many, many applications in medicine and material science devices and so on. And in this case, this is a quantum dot made of gallium arsenide, which we have simulated. And one of my colleagues in material science at USC, Anupam Madhukar, did experiments on that. Okay. The fourth one is vetting of substrates, and reactive in the sense that, there are chemical reactions taking place, okay, in this process. And that's a very difficult simulation, which we attempted, and it turned out to be very interesting. We have a very large effort in the area of fracture, okay, fracture of many, many different kinds of materials. And this is technologically, it's a very important problem. And these days, what we are doing is we are designing new materials where you can, in fact, stop the growth of cracks, and you can even, okay, heal the cracks. So, and this is a fantastic application, okay, for which we have separate DOE funding. Then I will describe to you nano indentation. That's a part of my talk. This is an approach where you take a atomically thin probe, and you look at materials and you can characterize their elastic and mechanical properties. So it's a very, very fine tool, okay, nano indentation, and it is usually done in atomic force microscopy. Then the next one is nanopixels, and nanopixels are, you have a substrate. In this case, the substrate is silicon. On silicon, you have a small pixel, which consists of silicon nitride. And this is, in fact, a device, okay? And this was also synthesized, and its characteristics were measured by Anupam Madhukar again at USC, okay, in a joint grant we have from DARPA. And then there is this hypervelocity impact. And in this case, you want to know what is the damage caused by a very high velocity object, small object, a nanoparticle. when it hits the surface. For example, this is a common problem, okay, in satellites and so on, because there is debris, impacting, okay, the satellites. And the question is what kind of damage it causes and how to mitigate that damage. And the last one is, we have a lot of interest in nanobiosystems. And in this case, we are looking at things like small interfering RNA, how do they go through cell membranes? And this is, this relates to cancer research. Okay. And so this is the overall program, but I would focus on one particular thing, okay, in this presentation. And that relates to a materials genome center we have at USC. And this is supported by the Department of Energy. Okay. And the way this happened, okay, is interesting. So in 2011, okay, there was this document that came out from the Office of Science and Technology Policy, White House. And the announcement was made by President Obama. And there was only one science picture, which you see in the middle. And it turns out that was a simulation we had done, okay, in 2002. I don't know how they got a hold of that picture, okay, but we were very happy that, it showed up in that document. And then, we got a phone call, okay, from the White House Office of Science and Technology Policy. They said, we want to do 3 meetings, one on the East Coast, one in the Midwest, and one on the West Coast, to generate interest in materials genome. This is a new program we are going to start, and the money is being allocated. And so we were asked to do the meeting here on the West Coast, and there were about 100 people, from various universities and industry which came to that meeting. And then 2 years later, this program was nucleated, and there was a call. They were all going to fund only 3 centers. So one center was funded at Brookhaven National Lab, the second one at Argonne National Lab, and we were the only university to get a DOE center in this area. Okay, and so I will describe to you what we do, okay, in this center. So it is called MAGIX, and the key institutions are, Stanford, Caltech, Berkeley, University of Missouri, and Rice University. And this is our team, okay? So Priya Vashishta, okay, he's also at USC, he's the director. And then, there are people like Ichiro Nakano, he's in computer science, he's a part of this team. And Oleg is in the chemistry department. And Malancha Gupta is in chemical engineering. She's an experimentalist. The other 4 people are doing modeling and simulations, okay? And from outside, at SLAC, at Stanford, we have 2 experimentalists, Uwe Bergman and David Fritz, okay? Really very, very fine experimentalists. And then we have Bill Goddard at Caltech, okay? He's a computational chemist. We have Kristen Person. She's in the materials science department, but she does a lot of work related to materials genome and machine learning. And she has a joint appointment at Lawrence Berkeley Lab. And David Singh is at University of Missouri. He used to be at Oak Ridge, okay, when we started, but then he moved to Missouri. And Ajayan at Rice University, he's one of the best in the world in making materials, okay? And he plays a key role in providing us the materials that we are interested in. Okay, so let me describe the kinds of things we do. And so we are interested in the synthesis of new materials in devices. And we do that computationally, okay? We do large-scale simulations, and I'll describe the kinds of simulations we do. And so these layered materials, we are only focusing on layered materials. So these materials are atomically thin. So their thickness is less than 1 nanometer, okay? And they're flat sheets. And these materials consist of things like graphene, for example, okay, which is very, very useful. Molybdenum-Disulfide, which is another very important material. And many others. It turns out,
what's the utility of working on layered materials? Is it easier to simulate? I mean, what's the need?
So there are 2 reasons. One, okay, so when we started the center, there were new materials, okay, and very little was known about them. But it was clear, okay, that these materials will be very useful technologically, okay? And also it turns out, because they're two-dimensional, okay, if you do a large simulation, let's say 1 billion atoms, you can go to the experimental times, length scales. Okay, so it was a very good, okay, synergy between experiment and modeling and simulation, okay? So these materials, when we started, they were a limited set of materials, but now there are thousands of their materials. The field has just exploded.
I see.
Okay. And so computationally, we try to find out what is the best way to synthesize these materials, okay? And after synthesis, we do experiments, okay, we meaning people at Stanford, okay, and at Rice University, they do experiments to validate our simulations. And once the simulations are validated, then, the software we have, we provide it to the community, okay? And that was the call, okay, when DOE wanted to fund these centers, that you develop software which will be used by the community, okay? And so we have done a lot of workshops and so on, okay? And so I will describe to you the things we are doing from the machine learning side on these kinds of materials. Okay, so the outline of my talk, I will first describe to you, okay, the kinds of simulations we do and the experiments. And the point of this is to indicate to you how rich this field is in terms of data, okay? And the second thing is then we go into the deep learning models. The models we have used are based on Hopfield neural network for associative memory. Now it turns out, I'm sure you are all familiar with these models, okay, Hopfield's neural network. It turns out these models really originated in physics, okay? And they, Hopfield himself was a physicist, condensed matter physicist. He used to be at Caltech before he moved to Princeton. And there he started to work in the bio area. And the neural network model that he developed is very closely associated with something, okay, related to spins. And these are Ising spins. And you have a D wave, and the implementation on D wave is Ising-like. Okay, so there is a very good connection between the two. And then from Hoffield's neural network, emerged, Boltzmann machines. And I will talk about the restricted Boltzmann machine. What we have done is application to the synthesis of 2D materials. And some of the work was done in collaboration with one of the students from computer science, Jeremy Liu, who is also here. Okay, so I will describe his work. And then we looked at crack propagation and phase transformations in 2D materials. And this thing was motivated by a beautiful experiment done at Rice University by our collaborator, Ajay. And in order to understand that, we did simulations, and then we modeled the data we got from the simulations using deep learning. Okay? And that was a variational autoencoder we used, okay, to model that. And then we are very excited about two things. Okay, one is this new neural network, which is equation learner. Okay? And we are using this to do two things. One, kirigami of materials. Okay, and kirigami is you take a material, you make cuts, and you make new architectures. So from 2D materials, you can make 3D materials by cutting and so on. And also origami materials. Origami is folding of materials, and these sheets are really like paper. You can easily fold them, okay? And UC started some of the work on folding of these materials, okay, when he was in our group. And the last thing is, we have huge applications, and so we are, developing an exascale deep belief network, okay, to model our data. Okay, so in terms of material simulations and experiments. So this part of the talk is to indicate to you, the kinds of data we get, okay, from simulations and experiments. So we use basically three approaches, okay, to do modeling, okay. And then there is, the fourth approach, which is sort of very well known in the material science community, so I did not indicate it. The most accurate approach is quantum simulations. In this case, you solve Schrödinger equation. It is a second order differential to solve for electrons. So it describes electronic properties, and it also takes into account how nuclei move, and so it is the most accurate description of materials. Okay.
But it's also the most computational.
It is very, yes, computationally very, very expensive. Okay. And so in our group, okay, we can do simulations on the order of 15 to 16,000 atoms, and that's considered very large. Then beyond that, because 15 and 16,000 atoms, okay, will only bring you to a certain length scale that may not be enough to reach experiment. Okay, then we have another approach which is called reactive molecular dynamics, and this one, what you do is in reactive molecular dynamics, you're basically solving Newton's second law, force is equal to mass times acceleration. Force is the important part, and so the force is derived from these quantum mechanical calculations, okay, which are done using a density functional theory at the bottom, and you take the force fields and use them in reactive MD. These simulations you can reach something like 10 to 20 million atoms. Now, beyond that, so in this reactive MD, chemical reactions are included. So if the bonds are breaking between atoms and so on, all of that is described, okay, quite well. Beyond that, okay, we have molecular dynamics, in which case reactions are not taking place. So, bond breaking and so on cannot be described, reliably. But other phenomena, okay, can be described very, very well with molecular dynamics. And these molecular dynamic simulations, you can do billions of atoms. Okay, the largest simulation we have done is 1.5 billion atoms, and that happens to be the largest simulation in the world. Okay, and so these are the three approaches. And if you want to go beyond, then you can even add on finite element. Okay, and then of course you can really reach experimental lengths. So we have also designed an approach, okay, and this goes back, okay, 10, 12 years, okay, where we can combine all these different approaches. So for example, if I'm looking at crack propagation in a material, so this one is crack over here. And so the thing is, if I go away from the crack, quite far from the crack, okay, then the displacement of atoms, okay, are harmonic, okay, and so one can use finite element, okay, far away from the crack. When you come close to the crack, okay, but not sitting where atoms, bonds are breaking between atoms, just a little away from here, there are nonlinear strains in the system, okay, and to describe them, well, we use molecular dynamics. But when you go very, very close to the crack tip, where bonds are breaking, then you have to do quantum mechanics. And we have developed a scheme where, we can embed, okay, in finite element, we can embed molecular dynamics. In molecular dynamics, we can embed quantum mechanical calculations. And this sort of bridges the landscapes. And this we have tested to make sure that the transitions between these different schemes are seamless, okay? And for example, in this one, this is a hybrid MD and finite element simulation in silicon. Okay, the lower part is MD, the upper part is finite element, and the two are joined by something called handshaking region, HS. Okay, and we send a stress wave through the system, and as you will see, okay, there are no reflections. It goes smoothly through the handshake region into the finite element, and the point here is that these schemes have been joined seamlessly. Okay. And this is the largest simulation, we have done, as I indicated to you before. This is for a composite. On the left-hand side, the red part is a silicon nitride matrix. Silicon nitride is a ceramic. It's a very hard ceramic, but it's brittle. In order to make it less brittle, but the strength should stay the same, we embed silicon carbide fibers. This is actually done experimentally also. And this composite, then we studied fracture in this composite, and it turns out it's really a very tough ceramic. And in this movie, you can see the reason why it is tough. The crack is propagating, okay? And as you can see, these things, the fibers are holding the material together. They're not letting it break, okay? And so you can apply very, very large strains, and the material is is still intact. Okay, and so as you can see from these, if you do a billion atom simulation, right? So each atom has 3 degrees of freedom, positions, for example, and then there are velocities of atoms, another 3. In total, you have 6 times the number of atoms. That's the number of degrees of freedom in your system. So one snapshot, when I do a simulation, one snapshot, that means at one instant of time, okay, I have 6 billion numbers, okay? And we run these simulations for millions of time steps. So you can see our data sets are huge. Then to relate to experiment, okay, there is this absolutely wonderful facility at Stanford, which is called Ultrafast Electron Diffraction Facility. And we work with our collaborators at SLAC, okay, Stanford, and they are doing experiment at this facility. It's an electron camera, so you put a material and you shine electrons on it. Electrons are diffracted from it, and when diffracted, these electrons give you information about where atoms are sitting in the material. And the resolution of this is less than 0.5 angstrom. That's how fine the spatial resolution is with this probe. Temporal resolution is less than 150 femtosecond. Okay, it's an amazing facility. DOE loves it. If you write a proposal and you say, I'm going to work with people at UED, okay, you have a better chance of getting funding. Okay, so it's a new facility, really beautiful. And they have done, very, very nice work to study time-dissolved, ultra-fast atomic and molecular dynamics in a variety of systems. Okay, and we have joint publications with people who have done experiments over there. I will show you one experiment, okay, which appeared in Science Advances. And this experiment, the material is tantalum disulfide. And in tantalum disulfide, you have electrons, and these electrons arrange themselves in the form of a wave, okay? And this wave is charged, and it is called a charge density. And there has been a lot of work done on how does the charge density wave in this material changes with temperature. So you're measuring resistivity as a function of temperature, and there are different regimes. And the question was, can you probe these different regimes? Resistivity versus temperature is an easy measurement. Can you tell where the atoms are sitting and how they're transforming, okay, using an experimental probe? And so this experiment was done, okay, last year. And what they did was they took the material, so the material is over here, and they just sent one pulse of electron, single pulse. And when you send a single pulse, it starts a reaction where the structure, which is called alpha over here, pristine structure, it begins to transform, and it forms 2 different structures in the same material, alpha and beta, and there is a wall between them, a boundary, which is called a domain wall. And it is the motion of the domain wall they were able to monitor through this UED facility. And then, interestingly, if you shine another, okay, send another pulse through the material, this material transforms back to the alpha structure. So as you can see, this can be used as a switch. Okay, just with one electron pulse, you can change the structure of the system and go from one phase to another. And with a domain wall, this domain wall with one pulse completely dissolves, and you recover the pristine structure alpha. And so this is this could be very good for data storage.
So the domain wall is stable, like once it forms, it's very stable.
If you don't do anything, then it's stable. Okay, but if you send one pulse, okay,
right,
that's it. Goes. All right. So these experiments, okay, on the right-hand side, I'm showing you a diffraction pattern. Okay, from this diffraction pattern, they, find out where the atoms are sitting and so on. And I have seen these data sets. These data sets are huge. I sat next to an electron microscopist, and he says, let me put my material and let me collect data, okay, for you. He put the material, aligned everything. 10 minutes later, he gave me 85 gigabytes of data on atomic. Okay. They have huge data sets. No, they analyze their data, but they do not model their data. Okay. And you people in AI, I mean, you know mathematical modeling of data. Okay. This is a data-rich area. These experimentalists who do electron diffraction and X-ray diffraction, they have a huge need, okay, to collaborate with people like him. Okay, so these are the two things. Okay, that's where the data is coming from. And then now let me describe, okay, deep learning models that we use in material simulations and experiments. So I'll just give you a very brief overview of what people are doing in the community. So I organized 4 focus sessions at the American Physical Society meeting in March. And this was on emerging trends in molecular dynamics simulations and data analytics. It turns out that 80% of the talk in 4 focus sessions were all on machine learning. I mean, the community, the physics community, material science community is very interested in this, okay? Because they have huge needs. Okay? And the kinds of things we heard at this meeting were phase transitions in materials, and I will describe that, okay, because we have also done work in that area. The second very important area in material sciences, when you're doing molecular dynamics simulations, the key element there is forces between atoms. How accurately can you calculate forces? Turns out that machine learning is doing a very nice job in developing force fields on the fly, okay, for simulations. And so I think there is a lot of room to make improvements, okay, but this is a very, very active area of research. The third one I also already mentioned to you, electron microscopy and X-ray diffraction, okay, and I will talk more about it. And then in chemistry community, they are also very interested in developing new kinds of molecules and with targeted properties. Okay, so this is Alain Esper's group at Toronto. They're doing really beautiful stuff using variational autoencoders and generative adversarial networks to design new kinds of molecules with targeted properties. Okay, so this is what is happening in the field. And now let me describe to you what we are doing. So I'll start with Hopfield network, okay? And as you probably know, in Hopfield network, you have neurons, okay? And these neurons have activity, which is described by voltages, okay? So, and then there is interaction between neurons, okay? And that's the synapse, okay? And the strength of the synapse is W, okay? And then there may be direct input, okay, coming from bias or current, okay? And so this is the basic building block of Hopfield network. Now, instead of neurons, you could have pixels. It's the same thing, so, in an image. Okay, so now to construct the network, okay, you have many neurons, okay, and they are all connected. So the Hopfield network will store patterns and can produce a pattern that closely resembles, okay, a new pattern. And so the way it works is, so this is a binary system in this case, and the algorithm is very, very simple. And it is, you look at overall input to a neuron, which consists of weights, okay, interactions with other neurons multiplied by the voltages, okay, other neurons, plus the bias current, okay. And if this quantity x sub j happens to be positive, you set the voltage of that neuron equal to 1, otherwise it is 0, okay. And you iterate this process by going over the neurons either randomly or in a system. And the thing that Hopfield showed was that this network, okay, this update process okay, decreases the energy. So the energy will continue to decrease. And he was able to write an energy function or a Hamiltonian for the system, which looks like this. And so again, it is interaction between different neurons, their voltages, okay, and mediated by the weights, and there is the bias term. Now this is the binary part. There is a so this is 1982, okay, when he did this work. And then he developed a graded response with continuous variables. Okay, same thing. Now in this case, the variables are continuous, okay, voltages and so on. And so the voltage then depends upon an internal function for each neuron. Okay, this internal function is x, okay, sub j for neuron j. And this is, the voltage depends upon this through a monotonic function. So, and this could be a sigmoid function, for example. And then the Hamiltonian, okay, is written over here. It has, this term was there before, this was also there before, and there is a third term, and which sort of describes that the response comes later, okay, than the applied external perturbations. And from this, what one can do is one can derive an equation of motion for x, and that is written over there. That is simply that dx over dt is the velocity, and on the right-hand side, it is the force derived from this energy. So it is velocity equals to force, and velocity equal to force means steepest descent. Okay? So that's what this is. When you do this, you start with a configuration. This is the energy landscape. Energy is always decreasing. So depending upon your initial conditions, what this network will do is find you the closest local minimum. And each minimum corresponds to a memory of the system. Okay? And so it stores memories in these local minima. Now it turns out that there are some limitations of this network. Okay? In order to address the limitations of this network, okay, recently, when I say recently, 2 years ago, okay, Hopfield and another person, Kalia, okay, they modified the model. So the energy function now, okay, is changed to something like this. And so this is, again, the voltage, and this is the memory. So there are k memories that you want to store, okay, and this f of x is a, power law, okay, and n is an integer. If n is equal to 2, you recover the previous one, okay, the one I described on the slide before. But they, they work with large values of n, 3, 4, and so on. And they found that this network, okay, works much better than the one before. And the reason it works very, very well is the following, that this model stores k memories, okay? The memories are denoted by this. When n is equal to 2, you can show rigorously that if you are trying to store random memories, rigorously, the capacity of the network is k max equal to, this should be 0 point, okay? 14% of the total number of neurons in the system that you can show rigorously. On the other hand, if you go to larger n, and they tested with things like n equal to 20 or 30, okay, it can store as many memory as the number of neurons. So this network is very powerful. And, when you're storing memories, you can store labels with them. And it turns out it does a much, much better job. Now, all of this work, okay, I want to just go back and mention this. In fact, this may be a better slide. If you look at this energy function, this Hamiltonian, and just focus on this term because that's the most important term. This is the bias term. It is an interaction, okay? It's a two-body interaction, voltage on J neuron, voltage on K neuron, coupled by this weight. Okay? Instead of voltages, you could have spins here. This could be spin on, okay, J spin, and the interaction between this, okay, mediated by a two-body interaction. And this whole thing, if you look at it, this is an Ising-like system, okay? That is spins interacting with each other, okay? And that's why this kind of thing works very, maps very well on D-Wave, okay, because it is isoclast. And the second thing is, all of this thing that Hopfield developed came from an area of physics which was very, very active at that time in 1982, and that was spin classes. So all of this has been borrowed from spin classes. It is coming from condensed matter physics and statistical physics. And that's what got me very interested in this area, because my background is statistical physics. I think statistical physics and deep learning are very, very closely connected.
So I have a question. This coupling, is it a sparse network or is it dense network? Does density matter?
So the one I described, okay, this one. This is a dense network. This is a very dense network, okay? But there are schemes I will describe to you where you can also bring in sparsity, okay, through L1 regularization, okay? We'll describe how that is done. Okay, so this is Hopfield network, and it turns out when he did this work at, at the same time, Jeff Hinton was getting very interested in this. And he, borrowed some of these ideas and started to work on Boltzmann machines. Okay, so now let me talk about Boltzmann machines. So Boltzmann machine, very simple. Okay, you have a visible layer where your data goes in. Okay, and then this visible layer is connected to one hidden layer. Okay, and there are no connections between visible units, there are no connection between hidden units, but there are connections between each visible unit to all the hidden units. Okay? And this network, if you look at the energy of this, the Hamiltonian of this network, it is very much like the Hopfield network. Okay, so you have a bias term associated with the visible layer. Okay, and you have a bias related to the hidden layer, and then you have interaction between visible and hidden layers, and these are, okay, this is very much like the Hopfield network, okay? And the beauty of Hinton's work is he came up with really very, very simple algorithm called contrastive divergence, okay, to update these weights. So in one step, okay, you can effectively update the weights. It works extremely well, but nobody really knows theoretically why it works so well. And so this is the thing that we are using. Okay. And it turns out there are two ways to implement, okay, restricted Boltzmann machine. One is based on probability distributions for visible and hidden units, and this is what most of the community does. Okay. And so you write down, the energy function, which depends upon all the visible units and hidden units. Data are the hyperparameters. And so this is the probability distribution. It has to be normalized, okay, so that when you integrate over V and H, okay, you will get 1. And to normalize it, you have to introduce this function, which is called Z, and Z is called the partition function. And this is very hard to calculate. So it turns out, if you look at it, this distribution, this partition function, this everything, it relates to statistical physics. Okay, so this is where statistical physics comes in, and we coming from statistical physics, we know many interesting and powerful algorithms to calculate this. Okay. Now this is what the community does. Okay, but in our implementation, we don't do this. Okay, so what we have done is, first of all, most of the work relies on these quantities, the data in the visible units and the data in the hidden layer, okay, has to be discrete, binary, okay. But what we have done is we have developed a scheme where the data can be continuous, okay, and the Hamiltonian of the system had to be modified, and so now the bias term looks like this, okay, for the visible layer. Hidden layer bias is the same. And this part of the interaction between visible and hidden layers is again the same. Okay? And what we do is from this, we derive a dynamical equation, okay? And we use that to update, okay? And that turns out to be a very, very powerful. It is extremely efficient. Okay? And that's what we have used, okay, to model some of the things. So now let me show you some of the results we have. So the first thing we did was we said, okay, one of my postdocs said, okay, let me try it on a celebrity image. Okay, so I don't know who she is, but okay, he took some image. And this is the original, and this is RBM training, and you can see as the number of epochs. This is in 1,000 epochs. This one is very, very close to that one. And you can see this image has a lot of features. Okay, but this scheme, okay, RBM scheme we have, okay, for continuous data, okay, with dynamical updates works really well. So this was for, for fun. And then I have a colleague at, a colleague and a friend at Sandia National Lab where I have a joint appointment, okay, and at the Nano Center. And his name is Barry Carter. So Barry Carter challenged. So he says, okay, I'll give you electron microscopy images, then you apply RBM on that and show me, okay, what happens. Can you do a good job or not? So next, he gave me this image. Okay, on the left-hand side is the original image. And with RBM, okay, this is what we get. You cannot tell the difference between the two. Okay?
I have two questions. One is, what is the advantage that this brings, and how is this better than other neural networks, like deep neural networks? Like, what is the outcome that this creates?
So I will show you. So this, at the moment, I have just shown you that it can reproduce images, right? The next thing is, can it provide you information?
Yeah.
Okay. I think that's the nature of your question, and that's exactly where I'm going. Okay. So this is just to convince you that RBM, okay, can reliably model experiment. This is experimental data, but having done this, now you can see this image has a mathematical description. Okay, we have a mathematical formula describing this electron microscopy. Okay, so now addressing your question. Okay, so now I will describe to you a few applications, okay, where I will take our data and model it with the Restricted Boltzmann Machine. Okay, and then I will show you the predictive power of this approach. Okay.
So just one question for them. So this Restricted Boltzmann Machine has some parameters data. So this is the results you're showing is the result of finding the optimal.
Right. After optimizing the hyperparameters.
You're training on the same image, or you're training on different images?
Different images.
Different images.
Yeah. We have done on thousands of images.
Right. And also the topology. I mean, so you having hidden layer.
Right.
Those are all parameters.
Oh, those are all parameters we can change. And it turns out, it's it brings up a very interesting question, okay, for computer science people. Let's say I have data. You put the data in visible, right? And now the question is, what is the optimum number of hidden units you should have, right? So it turns out, and correct me if I'm wrong, I don't think this problem has been addressed in the computer science community. But there is a way to address this problem through statistical physics. So the thing is, the ensemble I introduced, okay, if you go back. So over here, okay, this probability distribution, which is the Boltzmann distribution, okay, you fix V, you fix H, okay, and you find the right kind of hyperparameters, and okay, this is how this scheme works. So going in, you have to specify how many hidden units you have. It turns out if you modify this probability distribution function, this is Boltzmann distribution. If you go to something in statistical physics we call grand canonical ensemble, you can vary the number of hidden units, and the grand canonical ensemble will tell you what is the optimum number. And that's the way to do that problem. I haven't done it, but I know how to do it.
But that is provided that you know the distribution, right?
No, the thing is, over here also you assume the distribution is this. Okay? But in the grand canonical ensemble, the number of hidden units can change, okay, And the ensemble will ensure that when you are in equilibrium, because this is an equilibrium description, the correct number of hidden units will be there.
So to use grand canonical, for example, you need to treat those chemical things.
Yes.
So how to find?
So the thing is, you will specify, you will vary it, okay, until you find, okay, the lowest possible free energy of the system. That's it. In statistical physics, we know how to do it. I mean, the schemes already exist. Codes already exist.
Well, so you can do it for the molecular structure you were showing.
No. I can do it for any problem
For
you tell
any
me.
problem, for image?
You see, whether it's an image simply means pixel intensities, right? Atomic positions, okay, when I look at atomic positions, I'm photographing. I'm dealing with pixels and pixels.
So how do you specify grand canonical?
So the thing is, I will take the image and I will divide it up into pixels, and I will know the intensity of each pixel, and that's the data I would. Yeah, and that's the data I would. That is the input.
So what is the compression that you're getting here? So how big is the hidden units compared to the original image?
Oh, so the thing is, the results I just showed you, okay, and the number of hidden units, okay, now, of course, that also controls the error and so on, okay, but let's say if I have an image, okay, 32 by 32, 1024 pixels, I can model quite well with 64 or 120. Really well. And it is extremely fast. And it can do everything. The dynamical updates that we do can do everything that is probabilistic. Okay, so this is a material, okay, that we have computationally synthesized. So let me describe to you how we do. So we are doing molecular dynamic simulation. We just start with atoms. And so there are two kinds of atom, molybdenum and sulfur. Okay, we take these atoms and we describe what the forces are between these atoms, and then we do molecular dynamic simulation. Okay, and we are trying to make one layer of this material, just like you do in experiment. Okay, and the number of atoms is, about 4 million. And these are the system dimensions. It turns out when you make this material experimentally, it is very well known, and computationally we get the same thing. There are two kinds of structure. One structure we call 1T and the other structure we call 2H. As you can see, there are differences in this. For example, if you look at the molybdenum atom, which is this one, it is connected to 3 sulfur atoms. Over here, it is connected to 6 sulfur atoms. So there's a structurally they are different. It turns out their properties are very different. This system, okay, if you have this structure, it is metallic. Okay, so it conducts like a metal. This structure, it conducts like a semiconductor, okay, like silicon or something. So these structures have very different electrical properties. So we synthesize this structure, and then, okay, Jeremy, you guys know Jeremy here? No. Okay, so he works there, okay, and he, implemented RBM using this data, RMD data, on your machine. And it maps very well on your machine, it turns out. Okay. The problem he did was very interesting. He presented this at the American Physical Society, and his talk was very well received. So we gave him an image, okay? We gave him images of where atoms are sitting in this material, okay? And we took some of the atoms away. And we said, okay, he had some images with the atoms and so on, which he modeled using RBM. And then to test, we gave him these seed images where the right-hand side was totally removed, no information available. And we asked him to perform RBM and tell us where the atoms are sitting. So there's missing data information. He was able to get the right positions with RBM. And so this is very good for missing data. And this happens experimentally quite a bit. Okay, many times there are noise in experiments, and you don't really know where the atoms are sitting and so on. So this kind of machine learning approach can be very, very useful.
But there's no defects? There's no actual defects in this material?
Oh, there are defects, but you see, when the training was done on images with defects and so on. Okay, so that information is there.
Doesn't that correspond to a defect if there's a missing atom?
So this part, I think
there's a difference between missing atom and not having the data.
Well, I'm asking, can you distinguish this?
Yes. So if there were, let's say, defects, for example, in this region, RBM properly trained, okay, given this data set, will be able to put.
So the defects are not just so like a missing atom in actual material, missing atom is not
a defect. Yeah, it is a defect, right? Okay, but
this defect would have some effect on the other neighboring atoms. And
absolutely. Because if there were defects over here, then these atoms will not be sitting in these regular positions. Okay, for example. Okay. Because the forces between atoms would change and then. Okay, and then a second material. So this material, now instead of having just molybdenum and selenium, there is the third element, which is tungsten. And so our collaborator, Ajay at Rice University, he synthesized this material. And the way it is done is you have a substrate, and the substrate is sapphire, which is aluminum dioxide. And on that one, they deposited this material, okay, using a method called chemical vapor deposition. And this is an electron microscope image. And this image shows, okay, this is what they took at Rice University. They showed that in their experiment, there are two things. One, there is a matrix consisting of molybdenum and selenium. And in this one, there are patches of tungsten and selenium. This is a structure. So they took this material and they deformed this material, applied strain on this material. Cracks developed and cracks began to propagate in the system. And they had these kinds of images, okay, when the cracks were propagating. They came to us and said, this is what we see. Can you model it? And so we took this information from experiment and started to model it. And so I will show you the modeling part. So the modeling is this. We have one layer of molybdenum-selenium matrix, which is this black. And then there are these random patches of tungsten and selenium thrown in, okay, to mimic the experimental system. And we have a crack over here. And I'll show you a movie how the crack propagates in this. And what you're going to see is when the crack begins to propagate, this system is semiconducting. This is 2H. Everything is 2H. When the crack begins to propagate, it changes from the semiconducting to metallic phase. Okay, so there is a phase transformation induced by crack propagation in the system.
The practical implication would be a damaged substrate would destroy, I don't know, a transistor or something?
Right. But the thing is, the nice part, instead of destroying, supposing you want to switch between semiconducting and metallic, strain the system.
So it's not necessarily just crack, it's just a general
crack,
strain.
Just strain would do it. Okay. So, with strain, you can really change the electrical properties of the system.
Right, which also means it's a bit like, I forgot the word for it, but basically you can also measure very fine, like, forces this way, right?
Right. Okay. So this is a huge simulation. And so I will show you this movie, and when you see, okay, how crack propagates, you will see the transition from 2H to. The green region is 1T now. Okay, rest of the matrix is 2H. And you can see very interesting branches taking place as the crack begins to propagate and so on. And this is the stuff we want to model, okay, using machine learning.
Off topic, but is there a different energy in these two states? Can you use this to get some kind of energy out of the system?
The thing is, very good question.
Yeah,
very good question. It turns out that the energetics of the two states, 1D and 2A, they're very close in energy. Okay. But it is very clear that one is a metal, the other one is. So that property can be exploited to make devices by string. For example, there is a colleague of mine at USC, okay, and he is trying to develop, make new kinds of devices. So he's using some of these principles to make neuromorphic chips. Because you use very little energy to go from metallic to semiconducting.
You go back though?
And you can go back.
You can go back.
Yeah, you release the string.
Oh, I see. But once it cracks though, doesn't it?
No, crack we did because they use cracks.
Oh, okay.
But we don't have to use cracks. We simply have to strain without introducing any damage.
You can change molecular structure, right?
Okay, and then it turns out there are some very, very interesting structures, intermediate structures, that experimentalists have discovered using electron microscopy. So this is, again, the same material, okay, and there are intermediate structures which are called alpha and beta. Beta is shown over here, and in this case, in the beta structure, selenium atom, which is usually coordinated, that is, it is joined by 3 molybdenum atoms. In this case, in this beta structure, it is joined by 4, okay, atoms. And this one, alpha structure, you have zigzag chains of molybdenum and sulfur, which is totally distinct from 2H and 1T. It turns out whenever the material goes from 2H to 1T, you always have these intermediate structures which have been seen by electron microscope. And we see the same structures, okay, when we do modeling, okay. So this is again the crack propagation thing. And in this one, when we looked at the interfaces between 2H and 1T, we always found this alpha and beta structures. So we took this information, okay, from our simulation, and then we fed the data to a variational autoencoder, okay, and the encoder, okay, was able to identify in the latent space, okay, which atoms belong to the 1T phase, to the alpha structure, to the beta structure, to the 2H, and in addition, there are defects also. So then from the encoder, we went to the decoder, okay, and then we can use the information from the latent space to find out, how to combine this information to make new kinds of devices. So what we did was, we take information from here, find out where the atoms would be sitting from the autoencoder, and then we can create novel kinds of systems where you have, this is A equal to 0, which would mean, you only have 1T phase, and A equal to 1, just 2H, and in between you have different structures. And different structures, you will have this alpha or beta, you can put any one of them. So this information these structures are totally synthesized by machine learning. No other information after training. So machine learning is giving you these structures. These structures are devices now. And so we said, we want to find out how good are these structures synthesized by the variational autoencoder. So we did quantum mechanical calculations, which are the best calculations you can do, okay? Extremely accurate, to find out how robust are these interfaces and these devices. So we did two simulations. Okay, in one case we put the alpha structure between 2H structures. In the other case we put the beta between 2H, and we did a fully quantum mechanical calculation on these systems. Okay, and we found the atomic displacements were less than 0.18 angstrom, which is extremely small. In other words, what these quantum simulations are telling us is that machine learning is extremely reliable, and it can produce robust interfaces between structures, okay, and it can be used to make new devices. And so, back to my friend, Barry Carter. So he gave me this challenge. He says he took this data, electron microscopy data, and he says, I give you 5 images. Okay, so these images are taken the sequence of time. First one, then later this one, then this one, this one, and this one. And there are subtle changes taking place in these 5 images. He says to me, he says, I take this material, again, tungsten diselenide, 2-dimensional material. He says, when I bombard it with electron to see where atoms are sitting, the energy that I'm dumping on the material is changing the structure of the system. And I can take these snapshots, which are sort of separated by 1 second. And he says there are many changes taking place between these images, and I don't know how to find out what those changes are. He says, can you model this? What is happening? So that goes back to your question. Okay, can I predict what is happening between these images, okay, using RPM? So I said, fine. So we have developed an approach, okay. So now we have a time sequence of these things. So we had to, use this conditional RBM, okay. In conditional RBM, I will first describe the diagram. So the thing is, this is the visible layer, okay, where the data is sitting at time t. This is the visible layer where the data is sitting at time t minus 1, at t minus 2, and so on. So you can put many visible layers, and they have different sequences of time. So that data is available. So in Barry Carter's case, you can imagine this. He has an image at time t equal to 0, 1 second later, 2 seconds later, and 5 seconds later. And this image is now coupled to a hidden layer. Okay? And these, okay, the data in these visible layers are also connected to the hidden layer. Now, the connections are made in the following way. The energy function is modified, and this is again goes back to the work of Hinton. Okay? And so the bias term has this quantity A tilde. A tilde is now has the information about the data coming from visible layers before. And similarly, since there are connections between these visible layers and the hidden layer, okay, this bias B, okay, connected with the hidden layer, also have information about the data sitting in the visible layers before time t. And then, of course, there is the coupling between this and this. And so this is my Hamiltonian. I know how to train this Hamiltonian. I know how to find the hyperparameters W, B, and A tilde, okay? And this is the approach we will use to find, okay, what is happening between images. But this has to be augmented with something else, okay? And the something else is the following, you see? The challenge that Barry Carter gave me, he says, I will give you an image, let's say this one, at time t equal to 0. And this is 1 second. You tell me what is happening in between. So this is the missing data. I don't know what is happening over here, and I have to model it. So I'll feed unknowns over here, and I will optimize this whole thing to find out what is happening in the visible layer. So pixel intensities in this layer. And so to do this, we have implemented an approach where this conditional RBM is augmented by something called nudged elastic band. This nudged elastic band is a method used in statistical physics. And the way it works is the following. It says if you have a transition taking place between 2 images, okay, 2, states of the system, then what you can do is you can insert many unknowns in between. As long as you have an energy function, try to minimize the energy. Each one of the layers you have inserted in between, and all the layers are then connected through springs. Okay? So this image is given to me by electron microscopy. This image is given to me S by electron microscopy. All the others are unknown. I will connect them by springs. I will have a new Hamiltonian, which will be my RBM Hamiltonian that I just showed you, and these harmonic springs connecting these images. And I will try to minimize the energy of the system. We have done that, and it turns out it works quite well. And so now we are running these simulations for the electron microscopy images that Barry Carter has given me. And I don't have the results, but I'm confident, okay, that it will be able to. We have tested it on our data, and it can find missing images through this procedure. So, the point of this is statistical mechanics. There are many methods which are sort of very, very useful for machine learning, okay? Okay, so I'll just summarize this part of the work. So I've shown you deep learning models, okay, for computational synthesis of molybdenum-selenide. And I think, I hope I was able to convince you that RPM learns rules for underlying phenomena, and in this case, the phenomena going from metallic to semiconducting to metallic phase, and other kind of structural changes in the system. And then I showed you this variational autoencoder work, okay, also, and with BAE, you can synthesize new kinds of interfaces and new kinds of devices. And then the third thing I talked about was the missing data in electron microscopy and conditional RBM in large elastic band. Very useful. Let me spend the last part of the 5 minutes to tell you what we are doing, okay? And so all of the work that I described so far has been in interpolation. Okay? It turns out in machine learning, maybe you guys are all familiar, okay? But there is this extrapolation kind of machine learning approaches which are turning out very, very, very good. And I'll tell you how we are going to use material science. Okay, so kirigami. So this is a two-dimensional material, and in this two-dimensional material, I can make cuts. Okay, and by making cuts meaning I just remove certain number of atoms. This can be done, okay, using electron beams. Experimentally, you can introduce very, very fine features in materials. So the point of doing kirigami, that is cutting the material strategically, is to enhance the mechanical properties. So you can target a mechanical property and you say, tell me, where should I put these cuts and how many cuts should I make in order to get that targeted property? I think that kind of application machine learning is very useful. And that has been done. So what we are trying now is I'll show you a simulation where we deform this after introducing cuts, and we get the data from atomistic simulations, and that's what we will use to train a learning method. And in this one, you will see this material is extremely flexible. This work has been done by one of my students, Ben Wong, okay? And he's also doing machine learning on this now. So this is an indenter. This indenter is atomically sharp, and the whole thing that the simulation we have done can be done experimentally. Okay, and as you can see, this material is so flexible. Okay, and these are the kinds of materials that you will use for flexible electronics. So kirigami is turning out very useful in that context.
At the atomic level, though, is there potential for the atoms to refuse? Like, I'm just thinking.
Once you apply strain on them, they will have to respond.
No, I mean, say, if you cut those layers, can they also recombine? My motivation for asking this is like, I've heard if you, for example, have two pieces of metal in a vacuum, you can do a vacuum. I don't know if you
can join them.
Yeah, join them. So is that an issue here? I mean, are these cuts that work well in the simulation practical experimental?
So this part where the cuts are, let's say, on the scale of nanometer, 1 nanometer, there the cuts will not heal themselves. You will have to do something to heal them. Okay. And those kinds of cuts can be made by electron microscopy, by electron. So you take the material, put a mask, and then you shine electrons, and wherever the mask is not, that material will disappear. You remove the mask, and you've got this. So the approach we are using is this extrapolative equation learner. Okay, And this thing appeared last year, right? Have you seen this work? This one? It's really very nice. So the way it works is the following. So this EQL, okay, equation learner, is a functional learning network. So the data is you give X, okay, and Y depends on X. But we don't know what this functional dependence is, phi. And you may have noise in this one, okay? And so the thing is, what you want to find out, what is the analytical expression? Okay? It may be old. You've seen this one?
I think I shared something like that earlier today.
It's really very nice. Okay, so we are exploring. So phi can be, a set of ordinary differential equations, for example, that you don't know. Okay, and the way it works is it has two parts. So your input data goes in here. Okay, and there is a linear mapping. Linear mapping is very simple. You take W, multiply by Y, and add a bias term, just like we have been doing. And so then the data after linear mapping comes over here. And then over here, you feed them through nonlinear functions. And the nonlinear linear functions are identity operators, sine, cosine, and sigmoid function. And you can introduce other mathematical operators. So a datum here, okay, identity operator. Another datum here, and you'll take sine of that, and so on and so forth. And then you also have multiplication. So in the first paper, which, they only had multiplication, not division, but now they have also introduced division. And I think these, mathematical operators, unary operators, this list can be expanded. We can add more, okay? And I think it will become very, so it's a feed-forward network. It goes through many, many layers. And finally, you try to optimize it. And by optimization, you're trying to minimize size and approximation of phi, okay? And so this is the input data. So this is L2 minimization. And then you have a regularization term, okay, and which is the L1. And with this, and this is very easy to implement, okay? And we are using this approach to do the following problems.
Who is the name of the paper?
I will give you the name, okay? I should have put it on the slide, I'm sorry, but I will give it to you after the presentation. So what we want to do is folding. And this is an experiment done at USC, okay, by one of my colleagues. Really a fantastic experiment. And then my student, Ben, I asked him to do a simulation. So this is the simulation he just done. So what we are showing over here is, this is a sheet of graphene. And the idea is to fold graphene, okay? Well, by folding, you can make new kind of architectures. And this is water, okay? And we are applying flow of water from this side, and you will see this thing folding, okay? And I will run the movie, and you will see it. So the flow of water is coming from the right-hand side over here. This is yellow part is the flow, and you can see this sheet of graphene folding. This is a simulation. And experimentally, they see exactly the same thing. Okay? So we have, sent this paper out for publication. And so if you look at it, so I want to know what is the equation governing the folding of graphene. Okay, I want to find out what is the dynamical equation through equation learning. Okay, but if you look at this is like the movement of a robotic arm. It's no different. Okay? And they have, in fact, okay, the paper on this equation learner, they have, in fact, okay, done the motion of a robotic arm. The extrapolation part comes in the following way, that their input data was between, let's say, minus pi over 2 plus pi over 2 in the motion of it. Then they tested it, okay, for data outside that regime, that is minus pi to plus pi. Works beautifully. And then they had, for training data, they used a certain range of velocities. And then they went outside much beyond the regime where it was trained. Works very well. And it gives you a mathematical equation governing.
So how much data do you need to learn those functions appropriately? So generally,
if I have, let's say, tens of thousands of frames, no problem. And it's very easy to generate tens of thousands of frames, because typically we run simulations million frames. So we have the data, and then we will use this to model. So we'll use equation learner to model this. The second application we have in mind is the following. So this is another thing that one of my students did, and this relates to synthesis. And this is an interesting simulation. So I have a two-dimensional sheet of molybdenum-diselenide and another sheet. In between, I put this mixture of water and isopropyl. Okay? And this mixture is actually used to synthesize these materials. So when I put this mixture, I put one layer of it, and it separates, okay, into droplets, and that phenomenon is called de-wetting. And I will run this movie, and you will see this. And it has a very complex dynamic. So I want to use equation learner to find out what are the ordinary differential equations governing the dynamics of de-wetting. Okay, so as you can see, this layer, okay, as the simulation proceeds, it just forms, okay, these islands, okay, and in between, these regions are dry now. These are the wet regions, okay, so this is the de-wetting phenomenon. And then it settles down. I want to know what are the equations of motion for these interfaces, and I would like to find that through equation learner. And then same thing, I showed you phase transformation and crack propagation, and that's again something the equation learner should be able to find out how cracks propagate through the system and how the phase transformation from 2H to 1T, okay, that boundary moves, and that dynamics, I think one should be able to find. These are the kinds of things we are using, okay, to model with this extrapolative neural network. And lastly, our problems are huge. Our data sets are huge. And we really have to develop an exascale network, okay, to handle this. And that's not hard because, instead of having restricted Boltzmann machine, you have one hidden layer, and you can put many, many hidden layers, and then you have a deep belief network. And it parallelizes quite well, in fact, okay? And this is what we are working on. We're trying to put this very large-scale network to do, electron microscopy data, X-ray diffraction data, and our simulation. Okay? So with that, okay, I will stop, and thank you very much for your attention.
We are over time, but maybe encourage one question.
How much overtime?
Probably
20 minutes?
20 minutes. It was a fascinating talk, so that's fine.
I am sorry for that.
One question from
I got carried away.
Well, yeah, we'll talk.
Okay.
Hopefully, we won't be
Sure.
too much late.
Oh, we'll have a quick lunch, we'll show.
Yeah, so, that's really fascinating.
Let's thank the speaker once again.
Yeah.